Dear students, this is our 38th lecture on named reactions, and today we will discuss about Ene reaction, or this is also known as Alder Ene reaction. The Alder Ene reaction or Ene reaction, or this is also called as hydroallyl addition. This is basically an addition of an enophile to an alkene, that is called as ene, where we involve a 4 electron system, where we include this pi bond of the alkene and a allylic bond, CH sigma bond, and the pi bond of this allyl group, which is acting as an enophile. They will participate in a pericyclic reaction where this double bond will be created at this place, and this will add to this double bond, and this formation of carbon-carbon sigma bond will be there. So basically the Ene reaction is a carbon-carbon bond formation reaction, and the Ene reaction of any olefin which is having a allylic hydrogen atom is called as carbene reaction. So if we react alkenes with allylic hydrogen containing groups, then this will be called as carbene reaction. The Ene reaction requires high temperatures because of the high activation energy and stereoelectronic requirements, because this requires the breaking of this carbon hydrogen sigma bond, and sigma bond we know is a stronger bond, and this requires a higher activation energy to break this bond, and that is why the temperature at which this reaction takes place is often very high. Then the enophiles, they in addition to carbon-carbon double bond, which we can use is carbon-oxygen double bond also, or carbon-nitrogen double bond also. So aldehydes, ketones, or amines, they can also act as enophiles in Alder Ene reaction or Ene reaction. So basically in these types of reactions, the beta hydroxy or beta amino olefins, they are produced when we are using aldehydes or ketones. When we use aldehydes and ketone, we will get beta hydroxy olefins as the products, whereas if we use amines as the reactants, then we will get a beta amino olefins as the products, and these products formed, they may be unstable under the reaction conditions, that is at elevated temperature. Then they will undergo reverse reaction, which is called as retro Ene reaction. Reverse reaction means the reactants will be reproduced. Now similarly, if in the allylic system we are having a heteroatom, if this Z is a heteroatom, then the Ene reaction is called as hetero-Ene reaction. So the mechanism of the reaction will be same. Only thing is that this carbon in the Ene is replaced by some heteroatom like oxygen or nitrogen or sulfur. Then in reaction, as far as mechanism is concerned, the mechanism is same as we have seen in case of Diels-Alder reaction. All Ene reactions, they proceed via a 6-membered aromatic transition state. So basically, these are the four atoms here and two atom here. They will form a six-member aromatic transition state, and this transition state will transform into the products. The intramolecular ene reactions, they are fast than the intermolecular ene reactions, and here the enophile reacts with an ene component in a syn fashion. As far as mechanism of this reaction is concerned, that they will be in the same plane, that is syn fashion reaction will be observed. And because of the syn fashion reaction, the mechanism will be a concerted mechanism. So basically there will be a frontier orbital interaction between highest occupied molecular orbital of the ene component, that is the allylic part, and lowest unoccupied molecular orbital of the enophile, that is our alkene. So this interaction between these HOMO and LUMO of ene and enophile will lead to the formation of the products through a six-membered aromatic transition state. So basically the mechanism can take place in two ways, as we have seen. The first is concerted and a cationic pathway. So either through six-member transition state, or a cationic pathway is when these ene reactions, they are promoted by Lewis acids as the catalyst. Then third category may be a free radical mechanism, may also be seen in case of thermal ene reactions. So when the alkene reacts with a free radical initiator like diethyl azido dicarboxylate, then the process becomes a biradical mechanism. Now first, the concerted pathway, as I've told you, that there will be a molecular orbital interaction taking place between HOMO of the ene and LUMO of the enophile. So the HOMO of the ene results from the combination of 5 bonding orbital in case of vinyl moiety, and CH bonding orbital of the this allylic hydrogen. So there will be interaction between this HOMO and LUMO of the alkene. Then a concerted six-member transition state will be formed, which will transform this into the products. Now, as I told you, that all these reactions, they have high activation barrier, because there is a breaking of a sigma carbon hydrogen bond. And for example, in case of propene and ethene, we require almost this much amount of energy for breaking this bond. 138 kilojoules per mole of energy is required as the activation energy for the conversion of these two reactants into products in a thermal manner. So we can see that these reactions, they are high temperature reactions. But if the enophile becomes more polar, that is, instead of ethene, if we change ethene to formaldehyde, then its lowest unoccupied molecular orbital has a larger amplitude on the carbon. Then there will be a better carbon-carbon overlap, but there will be a worse hydrogen-oxygen interaction. Therefore, the reaction proceeds in an asynchronous fashion, and activation energy is lowered. So that means in those cases, the reaction will take place at a lower temperature. Then the order of activation energy in case of enophiles is that uh, alkene it is highest than amines, that is carbon nitrogen double bond, then carbon carbon double bond which is replaced by more polar groups like an ester group or carbonyl group or phosphorus group or sulfur group. They will keep on decreasing the activation energy in these reactions. Then second type of mechanism is that Lewis acids they can also catalyze the ene reactions, and here also the reaction take place through a concerted mechanism, but here the transition state is a polar transition state when the mechanism is concerted one. But if it takes place by stepwise mechanism, then there will be deuterionic intermediates which will be present. Deuterionic means there will be positive charge as and negative charge both present in the transition state. So for example, what Lewis acid will do, it will polarize the carbon oxygen double bond like this, and because of this oxygen will become electrophilic, and this will attract the electron density towards itself. Then it will lead to the formation of a six-member transition state. So this type of transition state will be more stabilized, because here this carbon is having delta negative charge and this oxygen is having positive charge. Similarly, if a stepwise mechanism is to take place, then deuterionic structure of this type intermediate is formed, and ultimately this will lead to the formation of a product. Uh, in general, the more reactive the ene or the enophile Lewis acid complex is, more likely the reaction is to follow a stepwise mechanism. So, if the ene or the enophile Lewis acid complex is less reactive, then the mechanism will try to be follow the concerted mechanism. Now this is one example of Lewis acid promoted carbonyl ene reactions. So here this is our ene and this is our enophile. So these are catalyzed by aluminium based Lewis acids. So aluminium catalyzed glyoxylate in reaction this is. So basically, if we see that there is a possibility of two type of transition states where there can be 1,3 diaxial or 1,2 diequatorial repulsions present in the transition state of the molecule, and we know that axial transitions, axial 1,3 diaxial repulsions, they are visualized more, and this will lead to so this is our 1,3 diaxial condition. These are less stable, and that is why we will be getting only minor product, or the anti-product will be formed as the minor product, and here we are having equatorial repulsions, and that is why this will be formed as a major product. Same product will be formed as the major product. Then third type of mechanism is radical mechanism. So in these types of ene reactions, we need to use some free radical initiator. And these types of ene reactions, if they are taking place thermally, then they will occur through stepwise biradical pathway. For example, if we take the example of cyclopentene, and what free radical initiator like diethyl azido dicarboxylate will do, that will create a free radical by breaking this sigma bond, carbon hydrogen bond, and we will get cyclopentene free radical like this. And then this free radical formed will react with diethyl azido dicarboxylate to give us this type of free radical, and this will then react with another molecule of cyclopentene, and we will get this type of product formation, and this is called as the radical mechanism for heme reaction. Then heme reactions, they can be intramolecular also. Intramolecular heme reactions are those where both the ene and enophile, they are present within the same molecule. So there are four types of substrates which can undergo these types of intramolecular ene reactions. So for example, if we are having carbon double bond, or this X and Y, they can be heteroatoms also, and we are having allelic system at this place, then this hydrogen will be transferred to this Y, and this will form a bond with this, and we will get these types of cyclic systems as the product. Similarly, if we are having these compounds in this orientation, then type 2 ene reaction, intramolecular ene reaction, they will give you these types of product. Similarly, if we are having these types of substrates where we are having carbon-carbon double bond and allelic system present in these types of stereochemistry, then the cyclization will lead to the formation of macrocyclic products. And type 4, which is called as Snyder intramolecular ene reactions, there the overlap between the enophile is largely controlled by geometry of the approach of the components, and this will lead to the formation of these types of products. Then some examples of regioselectivity, that if there is a possibility of formation of product at two places, two atoms, then out of those two only one is preferred. Such type of products, they are called as regioselective products. And one example is seen in case of Lewis acid catalyzed alkyl aluminum halides. They are the Lewis acids which are used as catalyst for such type of reactions. And here we use enophiles with the carbon oxygen double bond. So when these trialkyl aluminum catalysts, they react with enophiles and enes, then they will catalyze the formation of these types of zwitterionic structure, and then this zwitterions will lead to the formation of ene-adduct dimethyl aluminum chloride complex, which can further produce aluminum alkoxide and methane, and then the further product they can be formed. Then is some more examples of regioselectivity. So when this type of alcohol, substituted alcohol, where this allyl alcohol is protected by tertiary butyl dimethyl silyl group. This is reacted with this type of enophile, then hydrogen carbon hydrogen bond at this place will be uh, less reactive in comparison to the carbon hydrogen bond at the methyl group. So the transfer of hydrogen from the methyl group will take place instead of this CH2, and we will lead to the formation of this type of regioisomer. So single reaction product with more than 99% of anti-product will be formed when this reaction is catalyzed by this Lewis acid SnCl4, and reaction take place at minus 78 degree centigrade. Then the temperature also determines that which type of regioisomer will be formed in different types of reactions. For example, if we use this allylic compound with an alkyne of this type, this is a terminal alkyne. If the reaction is performed at high temperature of the order of 220 degrees centigrade, then 47% of this regioisomer is formed and only 3% of this is formed. Whereas if the same reaction is done at 25 degrees centigrade, then only this isomer is formed. So this also tells us about the regioselectivity of the Ene reaction. Then the Ene reactions, they can also lead to the formation of asymmetric products. So if we react these alkenes with malic anhydride, then there is a possibility of formation of products in two ways. One is that the transition state is formed in an endo manner, whereas other is the transition state is formed in an exo manner. But in exo manner, there is a repulsion between these bigger groups. Because of that, this will lead to a minor product, whereas this is more stable transition state lead to the formation of this major product. So basically, in case of such type of reactions, the endo transition state is preferred for the formation of this diastereomer rather than this diastereoisomer, because of the preference for the different types of steric effects which are observed in these two transition states. Now some examples of Alder Ene reaction. If we take the case of ethyl phenyl acetylene, the which is taken as an enophile, and this is the ene which is used for this reaction. When this reaction is performed in nickel based catalyst, nickel DPP bromide, that is 1,3 base diphenyl phosphenopropane group as the ligand, in presence of zinc metal and zinc iodide, they will in situ form a complex which will catalyze this Alder Ene reaction to give us Alder Ene products. Similarly, if we are having this Ene system and we have two types of alkynes present, where one alkyne is substituted by triethylsilyl group and other is by the ester group, then the preferably reaction will take place at the alkyne which is present at the end of the ester. Because this is more electron withdrawing in nature, and this will make this carbon more electropositive, and the attack of this will take place at this. And these reactions, they are catalyzed by ruthenium based complexes, and reaction take place at the room temperature, and product is formed in 81% yield. Similarly, in this allylic system, this carbon hydrogen bond is where the reaction will take place, and you can see over here when this alkene is reacted with malic anhydride in xylene, a thermal reaction when refluxed in xylene, then this type of six-member transition state is formed to give us this product in Alder Ene reaction. Then other example is 2-methylidene 2,3-dihydrofurane. This is the allylic system which is used as ene, and this is the carbonyl system used as enophile. So both of these, they will form a six-member transition state, and because of this ester group, this group becomes more active, and reaction takes place at very low temperature of the order of 0 degree centigrade, and we will get Alder Ene products. Sorry. Then some more examples of thermal ene reactions or Lewis acid catalyzed ene reactions. For example, when we are having this type of ketoesters, ketodiesters as enophiles, and these are the allylic systems. So they will form a six-member transition state at 140 degrees centigrade. In 16 hours, we will get 62% of this type of products through ene reaction. And this is basically an intramolecular ene reaction. Similarly, an intramolecular ene reaction can also take place. This part of the molecule will act as the allylic system, and this is our carbon-carbon double bond alkene, and in presence of Lewis acid, the reaction will take place at low temperature of the order of 20 degrees centigrade, and in 100% yield we will get a product of this type, where because of this six-member transition state and the stereochemistry of these two groups, this will lead to the formation of a chiral product. Then the Alder Ene reaction was also used for the synthesis of imidazo 1,2-pyridine systems or imidazo 1,2,3-iza 1,8-naphthydrane systems. And this reaction is called as SI reaction because here the nitrogen is involved in this reaction. So this system, SI system, when reacted with these types of alpha beta unsaturated ketones as enophiles, then basically the breaking of this nitrogen hydrogen bond will lead to the formation of this carbon nitrogen double bond, and this will attack this carbon double bond, and this bond will be shifted to this place, and you can see we will get this type of product, and then this will undergo this is the Schiff base or amine system, and hydrogen from here is removed and shifted to this place, 1,3 hydrogen shift, that is called as mean in amine tautomization. And then this can lead to cyclization at these places, 1H from here, 1H from here, and we will get this type of racemic product. And when we use an excess of methyl vinyl ketone, then the second mole of methyl vinyl ketone will further react with this nitrogen system, and we will ultimately lead to the formation of imidazo 1,2,3-IJ18 naphthydrine systems as the product, and this reaction is called as aza-ene reaction. So basically, the formation of these types of system requires two successive aza-ene reactions. First is this one, second is this one. So there are two aza-ene reactions taking place to give us these types of products from heterocyclic ketene aminals or reaction with enones such as methyl vinyl ketone. Then metal promoted ene cyclization can also take place to give us intramolecular ene reactions. This reaction is used for the asymmetric complete synthesis of alpha-canic acid. So for example, this part of the molecule acts as enophile and this part of the molecule acts as ene, and in presence of a chiral catalyst that is bisoxazoline magnesium perchlorate system, they react in situ to give us a catalyst which catalyzes this metal promoted in intramolecular cyclization to give us these types of chiral products. And here the ratio of cis to trans product is 20:1, and the product is formed in 61% enantiomeric excess. And then through different further reactions, this can be transformed into alpha-canic acid. Similarly, another example of intramolecular reaction is this, where this part of the molecule is acting as alkene and this is the allylic part. They will form a 6-member transition state using toluene as the solvent, and cyclization will take place to give us these types of amides as the product. Then the chiral titanium complexes, they have also been used for asymmetric ene processes. For example, the optically pure binephthol, either R or S binol, this is used in combination with diisopropyl titanium dioxide dihalide in presence of molecular sieve using dichloromethane as the solvent to give us these types of alderene products. And here we will get the chiral products when we are using the chiral catalyst. So the alpha hydroxy esters which are formed, they have high enantiomeric purity. This can be dependent on the halogen present and the type of the enantiomer which is used in the binephthol system. For example, if X is chloride and then the amount of catalyst, if we are using 10 mole percent of the catalyst, then the product of alpha hydroxy ester formed is 72% with 95% enantiomeric excess when the reaction time is 8 hours. Similarly, if we are using 1 mole percent catalyst, then the yield of the product is 78%, but enantiomeric excess decreases to 93%. Similarly, if we replace chlorine by bromine, if dibromo is used over here, with 10 mole percentage, the yield is 87% and enantiomeric excess is 94% and reaction time is only 3 hours. So all these factors they will determine that what will be the enantiomeric excess and what will be the yield of the product formed in such type of ene reactions. Then ene reaction can also be used for the synthesis of natural products like lolumelide, which is used as an anti-tumor agent. Uh, Here, one of the step which is used for the formation of this anti-tumor agent is Alder Ene reaction. So when this part of the molecule, that is compound A, is reacted with ethyl glyoxylate, which is acting as an enophile, in presence of binephthol, S-binephthol, and in titanium bromide they will form a complex, in situ complex, which will be chiral in nature. We will get uh, a chirality introduced at carbon 15 at this place. So a stereo center will be formed. So these are asymmetric Alder Ene reactions. And then this type of molecule on reduction of this ester group will lead to the formation of glycols, and then further steps will lead to the formation of lolimelide as the product. Then in uh, metal based complexes, also some chiral synthesis has been achieved, and mostly copper based complexes they have been used for these types of chiral reactions. So when ethyl glyoxylate is used with unactivated olefins, then we will get the alpha hydroxy esters as the products, and here again the products formed will be chiral in nature, and for these type of conversions we can use any of these three types of copper based catalyst, and depending upon the type of reaction used, we will get either this type of product or this type of product, or a mixture of these, depending upon the transition state formed by the reactants with these chiral catalyst, either catalyst 1 or 2 or 3. So basically we will get gamma delta unsaturated alpha hydroxy esters as the product with excellent enantiomer selectivity. So these are the references which have been used for preparing these lectures. Thank you very much.